I'm going to try to keep this lecture in 1 hour. Yeah, I still don't feel really well. Okay. So today we're going to move into a higher order nonlinear effect that's called third order nonlinearity. And by its name, you can kind of guess what it is, right? So previously we learned second order nonlinear effect, which means your nonlinear polarization, proportional to the square of your electrical field. That's called second order. You have two electrical field here. And then the third order, okay, means now you have three, okay, electrical field here, okay, e to the third. That's called third order nonlinear effect. And the basic equations of the third, actually of all the nonlinear effect are basically the same. You're solving the problem that you have an input on the left, nonlinear material in the middle, and then solve the output on the right. And then the electrical field, you can always, it's always written as a linear combination of different frequency components, and then each frequency components, their electrical field is location dependent. And then, of course, this is the general nonlinear equation. Okay, and the reason that we would like to talk about third order nonlinearity in addition to second order nonlinearity is not just because of mathematical interest, right? There's, the term here might look different from here. There are actually two major reasons that third order nonlinearity is actually very important in a lot of optical phenomena, for example, in telecommunication in fiber optics. The two reasons are, the first is that when we learned second order nonlinear effect, we said that, okay, if you look at this term here, it has even parity. You have E squared. That means if you flip the sign of your coordinate, the right-hand side doesn't change. Okay, but the polarization itself, because it's a vector, it has odd parity. Right. So if you flip the sign, the left-hand side can't equal to the right-hand side. That means your chi2 has to be 0 if your material has inverse symmetry. Right? Inverse symmetry means that when you flip your coordinate, your material properties stay the same. Right? So in chi2, what we learned is that your material, if you want non-zero chi2, you have to have non-inverse symmetry. Non-inversion symmetry. It's a bit small, but in chi3, the story is very different now. Chi3 here, because you have three electrical field multiplied together, so that this side also have odd parity. Right? If you flip your coordinate, you will acquire a negative sign. Okay, it's the same as your the nonlinear polarization. So what that means is that there's actually no material requirement for the third order nonlinearity. Okay, there's no requirement here. So for most materials, actually third order nonlinear effect is the first nonlinear effect it will see. Right? For example, for water, for glass, they don't have, they have inverse symmetry, so they don't have chi2 in it. So in fiber, optical fiber, the first nonlinear effect, for example, you will see is actually the chi3. Okay, so so the reason that we talk about chi3 is because it's more common than chi2, and then it appears in most materials. And then the second thing that we want to talk about what we want to focus on in terms of the nonlinear effect is that in chi2, we always say that there's phase matching. There's a phase matching condition, right? And the reason for that is because your frequency of light always changes. For example, if you have harmonic generation, of course, your frequency doubled. And then if you have some frequency or different frequency generation, your frequency always change a lot. And that's why you need phase matching condition, right? Because when your frequency is very different, then your refraction index is different, and the speed of light is different, then you will see the phase mismatch term here. So in Chi2, nonlinear effect phase matching condition is very critical, and it's whenever you try to do a second order nonlinear experiment, phase matching is the first thing you need to consider. Here for Chi3, I want to show you later is that phase matching condition is not always required. Okay, there are many special situations. Okay, that does not require phase matching. Let's say PM phase matching. And as you can imagine, okay, if an effect doesn't require phase matching condition, then it would be much more common than the effect with phase matching condition. So that means you don't have to actively adjust, or you don't have to precisely adjust or design your material, okay, to generate the nonlinear effect. It just happened to be there because the phase matching doesn't matter. Okay. And in the lecture note, in this class, okay, we'll focus in the next following lecture. We'll focus on the nonlinear effect that, in a broader sense, doesn't require strict phase matching conditions. Phase matching still matters in some sense, but then it's not like in second harmonic generation. And we'll focus on those phenomena. And what that means is that we don't care about third harmonic generation, as you can imagine, right? This one can generate e to the 2I omega t. This one, of course, can generate e to the 3I omega t. But because these two are typically the same mathematics, right? And then you need the same, this one is phase matching, this one is phase matching, and then the math is kind of identical, so we will not discuss, that the phenomenon that's kind of a duplicate from what you have seen from second harmonic generation, second order nonlinear effect. And then in page 2 on the note, there's some derivation of why there's no material requirement for the third order nonlinearity, and then basically it's the same as the parity argument, and I will not duplicate it here. You can look at it by yourself. Okay, and so first thing I kind of want to discuss is just to give you an idea of why in third order nonlinearity, in some cases you don't need phase matching condition. Okay, just give you an example, nothing general. Okay, and then later we will talk about the general case. Now imagine the simplest case that there's only one input. Okay, one input. One input frequency, okay, and then the third order, for simplicity, when discussing third order nonlinearity, we just ignore second order nonlinearity. Okay, you can make the argument, for example, if we do this experiment in glass, and there's no second order nonlinear effect, right? So you just erase this term. So okay. So nonlinear polarization is, okay, and again we neglect the fact that they're vector, and then just assume the electrical field are pointing towards the same direction. Okay, so this will be your third order nonlinear polarization, right? And then it has two components, right? So okay, so you have, for the E, okay, you have the positive frequency component, the negative frequency component, plus its conjugate. So that the electrical field overall is a real number, right? It's cosine. And so when we plug this in, you can kind of Okay, assume this is A and this is B, right? This part is A, this part is B, okay? And we know that e to the third, okay, now it's equal to A plus B to the third, and this will be A to the third plus 3A squared B plus 3AB squared plus B to the third, right? Basic algebra, okay? And then now we can look at, okay, what these terms are, right? This is the terms generated in your nonlinear polarization when there's only one input frequency, okay? So okay, so first term, A to the third is just E knob third. And then you have the frequency components, that's to the third, right? So apparently, this term is the third order harmonic. Okay, third harmonic generation, because you generate frequency components that's 3 times of your input light. Okay, and so you can also draw the same conclusion for the B to the third, right? B to the third is just E conjugate 3, okay, and then the positive frequency component, and then to the third, right? So you can say this is complex conjugate, okay, it's a B here. Now let's look at A squared B, okay, A squared B. So A squared B is interesting, it's because, okay, it's because if you think about what is A times B, okay, what is A times B? A times B is, because B is just the conjugate of A, right? B is just the conjugate components of A. So A times B is actually A times A conjugate is simply the amplitude square of A, right? It's simply the amplitude square of A. So here, 3A squared B, you can rewrite this as 3A times B times A, right? So as long as you have 2A in it, A, B, A, okay, it's the same as A squared B. So AB, we said, is just the amplitude square of A, and amplitude square of A is just E naught square, right? It's just the amplitude of this times A again, so E naught E minus I omega naught T plus I kz. Okay, so this term is very interesting. Okay, if you look at it, this is very interesting. The nonlinear polarization, okay, this term, the frequency and the wave vector is exactly the same as your input light, right? It's exactly the same as your input light. So what that means is that this term doesn't require phase matching condition at all, right? Because it has the same frequency, it has the same wave vector, it naturally matches everything, right? So when you plug this back into this nonlinear equation, this term just cancel out, right? The frequency and propagation term, okay, it just cancel out with each other, right? So this is exactly the reason, okay, why in third order nonlinear effect, some of the process does not need does not need phase matching condition. And you can do the same argument, same calculation for 3AB squared, and it will actually just be the conjugate of this term. Okay, just be the conjugate of this term. Okay, so here, just by having a single input, we have 2 types of terms. One is this is third harmonic generation. And in this class, we'll just ignore it. Okay, we'll simply say that, okay, phase matching condition, it's difficult to achieve if we don't do special design. So, okay, we don't have to consider this too. And then this term, okay, this term. Okay, let's look at it what it is. Later we will know, okay, this is actually something called Kerr effect. Or also it's, in this special situation, it's cell-phase modulation. Okay, so the way we keep, analyzing what this term really is, okay, is by plugging it back into this displacement field, right? Because displacement field, if you look at it, the linear components is proportional to your electrical field, right? And now in your nonlinear polarization, you actually have your electrical field again. It has a coefficient, right? So by plugging it back, you can actually combine terms. Okay. And epsilon, okay, epsilon r e. This term, okay, this term here is 3 epsilon chi 3 e naught square, right? E naught square is a coefficient you have in front of e term, also in front of the complex conjugate term, okay? And then times e. Okay, here e is the input with the negative frequency term, and then its complex conjugate. Yeah. So if you combine the common term, then what you will have is that you will have epsilon naught, okay, epsilon r plus 3 chi 3 okay. So now if you look at it, we know that the relationship, okay, the meaning of relative permittivity, right? Relative permittivity is is refraction index square. So what it looks like here, okay, what it looks like here is that the third order nonlinear effect change your relative permittivity that in effect will change your refraction index. Okay, if refraction index. So so we can keep doing this calculation and then assume that this term, okay, assume that this change, okay, of relative permittivity brought by the nonlinear effect is much smaller, much smaller than the material permittivity itself. Okay, if we make the assumption that we can calculate the refraction index, okay. Okay, first this is very standard, and then we can use the we can further write it down as epsilon r 1 plus 3 chi right. So you just move the epsilon r in the front and then leave everything else into the square root. And we're going to use this. We're going to use this approximation that when x is very small, much smaller than 1, okay, this is approximate to 1 plus nx when x is much smaller than 1. Right. And this one, you guys know, it's actually coming from Taylor expansion, that you do the Taylor expansion of this polynomial, and then if x is very small, you can keep the first term, okay, first two term, and this is what you get. So nr, okay, will be approximate to, would be approximate to, okay, 1 plus 3 divided by 2 epsilon r e squared. Okay, and we know that for the material itself, okay, epsilon r is the refraction index of the material, okay, square. Okay, so what you can do is that you can replace this as refraction index naught. Okay, naught means that when there's no light input, okay, just the intrinsic refraction index of a material. Okay, so so this way, okay, you can see that your input light through third order nonlinear effect, okay, change your refraction index. Change your refraction index, and also this, you know, right now, okay, this expression, okay, in the mathematical sense is complete, but it doesn't really connect to experiment, because experiment we don't really we don't really measure electrical field. Instead, we measure power or measure intensity. Okay, so to further, you know, transform this equation to something that you can compare with the experiment, what we are going to do is that we're going to use this, you know, power equation for the electromagnetic wave. That is, okay, I think we used this before. Okay, so one thing notice here is that the definition here, okay, the definition of E. So if we do definition in this way, the net result will be 2E naught cosine omega t plus kz, right? So there's a factor of 2 here if we make this definition. We choose this definition is because, you know, we don't want to carry the 1/2 around, right? In some books, it would define the electrical field as E naught cosine omega t plus kz. In that way, you have to carry 1/2, okay, throughout your calculation. And normally this is not a problem because, like, because it's just 1/2 factor. Okay, you can introduce it anywhere. The only place where that start to cause problem is this. Is this when you calculate power? Okay, when you calculate power, you have to take E squared. Okay, E squared, and so that factor of 2 really matters. Okay, that factor of 2 really matters. So if you miscalculate it, you can be off by a factor of 4 in terms of a power. Okay, and power is something you actually can measure, right? So the definition here, you have to be consistent. I haven't checked it this time, but I think I checked it when I wrote this note. So if I use this definition for electrical field, the power will be look like this. Okay, the power will be look like this. Okay, and also, like when you're reading books, and if you find the power expression is not this, okay, check their definition of electrical field. Okay, so if we use this, then what we can get is that we can write down E squared, okay, as power divided by, let's see, okay, E squared, okay, equal to power divided by mode area, okay, the area you have, times, you know, the reverse of all this coefficient. Okay, reverse of all this coefficient. So now you can plug this in, okay. We actually call this n naught plus delta n. Delta n is the change of refraction index. Okay, if you plug it back in, okay, plug it back in, and notice that the P divided by A, what is this? P is the power per unit time. Sorry, it's the energy. Okay, power, okay, P itself is power. Power is the energy per unit time, okay? And if it's the energy per unit time per unit area, okay, that's intensity, right? If you focus the power, in a very tiny spot, okay, the amount of power is the same, but then the intensity becomes very high, okay? So this is intensity, okay? So you can see that this effect, okay, will be related to intensity, okay, not just power. If you focus the light a lot tighter, then this effect will be a lot stronger, okay? So if you plug it back in, and then what we will see is that the delta n, okay, and then I would neglect, a lot of math here. Delta n is 3 chi 2 epsilon r, okay, c times intensity, okay? So your refraction index change is proportional to intensity. And people usually write it in a very simple form as the refraction index is the original, okay, the intrinsic refraction index plus N2 times I, okay? And N2 is this coefficient in the front. And then in experiment, usually people directly measure this N2, okay? There are several ways to measure this N2. And we'll actually later talk about it, okay? And this effect is called Curd effect. Okay? It's that the refraction index is a function of intensity of light. And for most materials, I think it's for all materials, N2 is larger than 0. Okay, N2 is larger than 0. You can kind of look for reasons why, okay, it is this way. But just a pure observation, okay, it's larger than 0. Any questions so far? Okay, I think I can get rid of this. And if you turn to page 4 on your note, I'm not going to write down, write them down on the board. If you turn to page 4 on the note, there are a few observations of what we have just did, right? The calculation. The first, of course, very obvious, is that your refraction index change with the intensity of light. Okay, and then the second thing is that throughout this calculation, we actually didn't really use phase matching condition. Okay, there's no need for phase matching condition for this Curd effect to happen. Okay, later we'll modify this statement. Okay, the third is that this whole thing, okay, this whole calculation is based on the situation where the input light is a single frequency. Right? We really haven't touched the case where you have multiple frequency components, right? So a natural question later, okay, we're going to solve in this class, or at least discuss in this class, is okay how this equation would look like when you have multiple frequency components as your input. Okay. Okay. Now a more general question is that, okay, is this useful? Is this useful in any way? I guess last week we talked about that people use electrical field to change refraction index. That's the electro-optics effect, and then people actually use that to to make phase modulator and then intensity modulator that really, is of extreme use in the telecommunication. Now, now, if you look at this equation, it looks like you can do the same, but it's an optical modulator. Okay, it looks like instead of using electrical field to control the refraction index, you can use a light, right? You can use light to control the refraction index. Okay, then you can start to make optical modulators. And also optical switch, use light to control light. And so here we're going to do some very simple calculation and see if that's possible. Okay, and the basic principle here is that if you have light input from the left, okay, and the input is the same as a single frequency input. Okay, and then you have Coulomb effect, okay, nonlinear effect here, that your refraction index change, okay, from n up to, related to its intensity, okay, and then the length is L, and then at the output, because we know that the frequency did not change in this case, what's the only thing that changes is the refraction index, right? And the refraction index is coupled with your wave vector, right? Wave vector is 2 pi n, okay, divided by L. So that if you change your refraction index, you change your wave vector, and then you change your phase after this propagation. Okay, so the output would be, okay, still you have the same frequency component, and then we'll say K knob is K knob is 2 pi n knob, right? The original intrinsic refraction index divided by L, sorry, divided by lambda. Okay. Okay, plus the added refraction index change. Okay, so you have two components, K naught and delta K. So here you have K naught L at the output, okay, times additional phase. Okay, additional phase. And we know that to make this effect really obvious or observable, one way that you can one way that you can observe the phase change is through interference, right? So if you have a line, you split into two paths, and in one path you have this meteor there with Coulomb effect. In the other path, you don't have any meteor with Coulomb effect. For example, you propagate in vacuum, and then you combine them, right? Then the output would be, this is input, okay, and the output would be, okay, you will have right, this is what the wave would be if you don't have the change in your refraction index. So this path, nothing changed, plus this path, you have a change of, right. Okay, so this is what it would look like. And we know that if delta KL equal to pi, right, then this term becomes -1, and 1 minus 1 is 0, right? So you have interference that's dark. You don't have any output here. And if this phase term is very small, then it approaches to 1, okay, then the output is the same as the input. Okay, this plus this give you cancel out the 1/2 here. Okay, so let's use a real material that kind of everybody use in the lab to estimate, okay, how strong this effect is. So the material we're going to use, of course, is glass, right? It's like the components of fiber, okay? And in fiber, how strong is this N2? Okay, this N2 called silicon. Two times 10 to the 20, okay, meter square per watt. Okay, meter square per watt. And it doesn't look good, okay? From here, it's very small. And what is the usual intensity of light you can achieve? Here we want to, well, of course you have many different type of laser. You can, this can vary a lot. But here what we do is that we, okay, confine ourselves in the eye safety level. That's 5 milliwatts in terms of power. Okay, and then what is the mode area, okay, of your light spot? Here what we can assume is that, okay, we're just using fiber, right? Fiber is roughly, the diameter is 8 micron, okay? And then if you calculate the area, it's on the level of 100 micron square, right? It's pi times a square, okay? It's 100 micron square. And so if you plug in the numbers here, this is 5 times 10 to the minus 3, okay, this is 10 to the 2, okay, times 10 to the minus 12, okay, and you're at 5 times 10 to the 7, okay, watt per meter square, okay, per meter square. So it's actually quite large, and the reason that it's large is because you focus the light very tightly, okay. So now we can estimate this delta n now. Okay, delta n. Delta n is n2 times I. Okay, and then you plug in this number. 2 times 5, okay, times 10 to the 20, times 10 to the 7, okay, and then this gives you 10 to the 8. Okay, in total it's 10 to the minus 12. Yes, 10 to the minus 12. So this is, okay, how much your refraction index has changed. Remember, refraction index, the typical value is between 1 to 3 or 4, right, if you use different material. 10 to the minus 12 is really, really a small number, okay. Nevertheless, okay, if let's say we really want to do this experiment and observe the interference, okay, then our question is, if you really want to observe this interference, you have to have your phase change delta KL equals to pi, right? That's how much phase change you need. And so now the question becomes, okay, then how long the fiber has to be if I want to observe the interference effect coming from the Kerr effect, right? And if you do this, then this is 2 pi delta n divided by L divided by lambda, okay, times L. Okay, and then you cancel all the common term here, and then L become lambda divided by 2 delta n. Okay, 2 delta n. And so let's say we do this experiment in telecommunication wavelength, right? That's why we use fiber. In telecommunication wavelength, the wavelength is usually 1.55. Okay, we can drop the other 1.5 micron. Okay, and then you have the refraction index change is 10 to the 12. Okay, and then 1.5 divided, it's not that different from 2. Okay, so if you just calculate the order of magnitude, then this is 10 to the minus 6. This is 10 to the minus 12. Okay, so meter. Okay, that's okay, 1,000 kilometer, okay, and just give you an idea, this is roughly 600 miles, or 10 hours of driving. That's basically the distance between Charlottesville and Orlando in Florida, or Charlottesville and Boston. Okay, so you will not want to do this experiment. Okay, and okay, so what that tells us is that although Kerr effect exists, and we can magnify in some cases that make it extremely useful for certain cases, but you probably would not want to use it to build a modulator or optical switch, right? Because either you need very intense power or your very intense laser, right, to have high power, small area, okay. But then even in that case, you still need really long interaction length, and also like anytime you want to build a switch or you want to build a modulator, the goal would be you want to switch the status of your device using as little power as possible, right? So if you need to use using as little energy as possible. So let's say if your switch itself, okay, need 1 watt to operate. And now imagine if you have 1 billion switch, right, to do a computing or to do something that would consume gigawatt power, and none of us can afford that. Okay, so Kerr effect. Okay, so the conclusion is that you need high intensity, okay, for that to be apparent, and then in other cases you can kind of just know it's there, okay, but then unless it's necessary, you don't have to account for it to have a significant impact on your experiment. Okay. Now let's talk about some of the applications of Kerr effect. Okay, and then I want you guys to know, okay, why Kerr effect actually is the reason that I don't know if you guys heard of the surgery called LASIK, is to to change to actually polish your the lens in your eyes, and then to to, like, for people like me with short eyesight, you don't have to wear glasses anymore. Okay, and Kerr effect actually is one of the reasons that experiment is possible, and I can explain to you guys here why. Okay, so the very famous probably one of the most famous effect from Kerr effect is something called Kerr lens. I think I can erase this. Kerr lens. So I will just introduce it here just to give you guys some idea that Kerr effect is useful. I'm not going to go into the details of the math of Kerr lens. Okay, so let's ask ourselves the question. Okay, what is a lens in the first place? Right? We all learned this probably in middle school, that the lens, okay, if you have, for example, a piece of glass n larger than 1, right, you put it in air, then this lens is a focusing lens. Why? It's because we know the the upper half, okay, will have a shorter optical path. Okay, shorter optical path because it's thinner, right? So, and the middle part would have the longest optical path because of it's thicker, right? So in effect, because we know that the light tend to travel at the same optical path, or the maximum or minimum optical path, okay, then this lens will become, a focusing lens. Is because this is the way, okay, when when the light here have less optical path, it compensates by, focusing, right, to here and traveling more distance. Okay, this is how a lens work. Okay, and now think about this: is this the only way that we can build a lens? Actually, the answer is no. Right, the lens work is simply because the at the position of the lens, in the middle, the optical path can be defined as the optical path is defined as the refraction index times the length. Okay. You can do actually the same thing with the planar structure. Okay, with the planar structure. Now suppose in the middle, your refraction index is larger. Right. Okay, this is x direction. Refraction index. Okay, imagine in the middle your refraction index is larger. And on the edge your refraction index is smaller. Okay. Then this structure is equivalent the same as this structure, right? Because light in the middle will have more optical path, right? More optical path than the light on the edge, right? So effectively, this also become a focusing length. Okay, become a focusing length. And now think about how Kerr effect can create a lens. Okay, so when we draw this lens figure, right, and also when we actually draw any figure that light propagate, we kind of assume that it's a plane wave. But for any one of you who have used a laser beam, right, the laser pointer, you know that laser light is not a plane wave, right? Laser light actually usually is a Gaussian wave that in the middle of the beam, it's very high intensity, and then the surroundings has less intensity. Right. So if you do a cross section, okay, this is x and this is intensity, you will see that in the middle, okay, the intensity is highest and then slowly decay onto the edge. Right. This is a very typical laser beam, as any beam, right? It must have a focusing point. Okay. And now because of Kerr effect, okay, n equals n up, n2 times intensity. So it's very obvious now that when you put a Gaussian beam, okay, into a Kerr media, then what will happen is that in the middle, the intensity of the light is very strong, and so that the refraction index is actually higher in the middle. On the edge, your intensity of light is much weaker, and thus the refraction index is smaller. Okay, so the fact that your beam has a center, okay, has a center spot, and the fact that the refraction index change with your intensity, okay, naturally give you a lens structure. Okay, and this is called Kerr lens. It's a lens that created by Kerr effect. Right, Kerr effect. And this is actually observed in experiment, is that by using very high power laser beam and then shining into a piece of materials. And what people would see is that at first, okay, what people would see is that, okay, this type of lens is actually focusing lens, right? So, okay, if you have a piece of media here, and then you have, like at the beginning, this is the size of your light spot, okay? And what will happen is that because of Kerr effect, it creates a focusing lens, and then the beam will try to become narrower and narrower. Right, so it's actually creating a self-focusing effect. And as you can see, okay, when the light beam is become focusing more, okay, spatially, the intensity must increase, right? Because intensity is just power divided by your area, right? And then the power, there's no loss of power here, and then as the area decreases, okay, the intensity becomes much, much stronger. So this effect will keep going, become more and more intense until it balances with the diffraction effect. Diffraction is when you try to focus the light tries to spread out, right, because there's a wavelength. Okay, for example, you can't focus light better than the size of a wavelength. That's because of diffraction. So eventually, okay, this would balance out with the diffraction effect, and from a large beam, it's autofocus to a small beam. Okay, this is something called curve length and also called self-focusing effect. Okay, and people actually figure out a very clever way to use this curve length effect. People actually use it to create something called femtosecond lasers. Femtosecond lasers is a key component in LASIK surgery. Okay, femtosecond laser means that the laser pulse, okay, laser pulse that has a duration, okay, as short as a femtosecond scale. Okay. So this is time domain. Okay, if a laser pulse delta t, okay, is around several tens or hundreds of femtosecond, okay, that's called femtosecond lasers. And how people create femtosecond laser with this curve length, okay. This is actually very clever, and then if we read into the history back in the 1970s, this actually was discovered by accident. People build this, and then somehow there's a curve length in their system, but then I think the experimentalists didn't realize that, and then they also didn't know. And actually, in their original paper, I think it's optics letters or PRL. They actually describe that in order to start their femtosecond laser, they need to hit the table, okay, and later, okay, people realize it's actually some other effect that actually generate this, okay. So how can we make the curve length effect into a femtosecond laser? The idea is very simple, okay. Suppose this is a black box, okay. Suppose this is a black box of curved media. And then on the left, you have input line, right? And then let's say a certain size, this is a beam size, okay? And now imagine, okay, if this is high power, high intensity, high intensity. High intensity, high power, kind of the same thing, high power. Then if it's high power, then on the left-hand side, okay, the light beam will be focused, right, will be focused. And if this is low power, then the curve focusing effect would be much weaker, right? Because the refractive index change is proportional to the power you have, and you actually have a much larger beam, right, at the output. Now imagine now at the output port, I put a spatial filter. Okay, you can imagine. Okay, this can be just a black piece of black paper with a small hole inside, okay, small hole in it. So what it can do is that it only allows the light in the center to transmit, okay, and then block all other light. Block all other light. Then now this is create a very interesting scenario is that if you have high power, then the light will be much more focused, and then they are more likely to transmit through this small hole. If you're low power, then your light is more spread out. Then a lot of them will be blocked, okay, by this black paper. Okay. Then, in a way, okay, we can say that for high power input, this configuration with curl lens and some, absorber with the hole inside, for high power, you will have low loss, right? Because most of light can transmit in the middle. And for low power, you will have high loss because of a lot of light are spread out, okay, around and are blocked, okay, by this structure. So this is something called saturated absorber. Okay, saturated absorber means that if your power is very high, then your absorber is saturated and no longer absorb light. Okay, and if your power is very low, okay, then your absorber is not saturated. You have a lot of you have the capacity to keep absorbing light. Okay, and if we kind of write down the absorption coefficient, it will be original absorption coefficient 1 plus I intensity divided by critical intensity. That means if you look at this equation, okay, if I is 0, that means you have the absorption coefficient that's the same as your original material. But as you increase the intensity of light, okay, more and more light are focused at the center, then you have less and less absorption. Okay. Now, how is this going to be useful to create a thermosecond laser? Okay. Now, you can put this saturated absorber, okay, in between a pair of mirror, or you can put the saturated absorber in a laser structure. Okay. Now, think about this. Now, when light is generated in this system, you typically have two options. One is that you can generate some pulse light, right? Pulse light. The other is that you can have some continuous wave, okay? That the light is the light is continuous. And for a typical laser system or for any system, the overall power is the overall power is a constant, right? It's like how much energy you pump into your system. So for the pulse light, because all the energy is focused at one spot, so this will have much higher intensity. Higher intensity and higher power. And for this, higher peak power. And for the continuous wave CW, it will have lower peak power or lower intensity. Okay, so it now become very clear. Okay, for laser system with saturated absorber, a pulse light will have lower loss, and a continuous wave light will have higher loss. And we know that in a physical system, okay, when given a choice, the system would tend to go to the state with higher efficiency, okay, or it would tend to go to a state with lower energy, which is more stable. Okay, so in this sense, if you put saturated absorber into a laser system, the system would naturally favor a pulse light because it has lower loss. Okay, the system is more stable, is more efficient, has lower loss. Okay, that's why how the Kerr effect and Kerr lens can be used to create thermosecond lasers. And back to the story why, okay, at the very first experiment of the Kerr lens thermosecond laser, why people need to hit the table, okay, to start the laser. The reason is very simple, is that they need to create a strong enough perturbation, okay, to make this current effect large enough to initiate this current length. Okay? If it's just continuous wave, the current effect is so small you will never actually reach a threshold for the current length to be significant enough. Okay? If you hit the table, okay, and then the laser is interrupted, and there's a sharp dip, and then this sharp peak will actually evolve into the thermosecond pulse. Okay, and nowadays, okay, people actually don't hit the table anymore. There's a shutter, okay, in front of the pump that you close it, open it, and then create a perturbation that's strong enough to initiate this current length. Okay, initiate this thermosecond laser. Okay, that's all for today. And then next week we will start to talk more details, more math, okay, about the third order nonlinearity effect, and especially current effect when there's more than one input frequencies. Okay, and that's it. Thank you.